This is a lecture on series parallel pipes and minor losses. And let's take up series connections and the equations that are necessary here, parallel connections, and minor losses from fittings and connections. We'll discuss more on this as we move along. So let's have series parallel pipes, and let's define parallel pipes first. So two pipes are parallel if they separate at one junction and meet again in another junction. So let's have this situation here. So we have two pipes, 1 and 2, that separate from junction A and they meet again at junction B. So these two pipes, regardless of the direction, as long as they separate at one junction and meet again in another junction, then they are said to be parallel. So if we imagine a piezometer attached at junction A and a piezometer attached at junction B, because the energy grade line is common for the two, therefore we say that for parallel pipes, the head loss is the same. So the head loss in pipe 1 is equal to the head loss in pipe 2. So this is the common head loss. That's the drop in the energy grade line in these two piezometer. And before the junction, of course, they have the same velocity heads. So that's why the drop is the same. So pipes 1 and 2 are parallel. The head loss for parallel pipes is the same. So HF1 equals HF2. Then for the division of flow, if the discharge entering a junction is Q, then it will be equal to the sum of the discharges leaving the same junction. So for series pipes, the discharge into a junction equals the sum of the discharges leaving the junction. So this single pipe here is in connection with these two parallel pipes, but they are in series. So that is Q equals Q1 plus Q2. So for two pipe systems to be equivalent or equal, they must have the same capacity, so they must have the same discharge or volume flow rate, and they should have the same head loss. It's for two pipe systems to be equal. Then let's now have pipes in series, neglecting minor losses in the connections, such as the presence of conical, we have gradual contraction here for connecting pipes. Then we have pipes 1, 2, and 3. Naturally, we call the junctions as A, B, C, and D. So Q1 equals Q2 equals Q3, and so on and so forth. So the discharge is the same. So Q equals Q1 equals Q2 equals Q3 equals dot dot Qn for flowing liquids. And that's from continuity equation. And for the total head loss from junction A to the last junction, then it is simply the sum of the individual head losses, friction losses. So HF1 plus HF2 plus HF3. So that's for series pipes. Then we have series parallel pipes, case 1. Then in this situation here, notice that pipes 2 and 3 are parallel because they separate at junction B and meet again in another junction C. So for the flow rate, Q1 equals Q4. So Q equals Q1 equals Q4. And Q1 equals Q2 plus Q3. There's no need to set up Q2 plus Q3 equals Q4. That's a redundant equation. So since pipes 2 and 3 are parallel, then HF2 equals HF3. Then for the total head loss, it is HF1 plus HF2 plus HF4. Now you can use HF3 instead of HF2 because they are equal. So that's it. So for series parallel pipes case 2, so we have here a situation. Actually, this is the same as before. That is, for discharge, Q equals Q1 equals Q4, and Q1 equals Q2 plus Q3, and pipes 2 and 3 are parallel, so HF2 equals HF3, and therefore the total head loss is HF1 plus HF2 plus HF4. So which is the same as before. It's only the drawing that is changed a little, but actually it's the same as case 1. The next case, series parallel pipes 3. So notice that pipe 2 is laid parallel to combined 3 and 4. 3 and 4 are in series, but they separate at one junction, meet again into another junction. So for the discharge, these are the equations. Q1 equals Q5 equals Q. Q is the total discharge entering the system, and it is equal to Q1 equals Q5. Then Q1 equals Q2 plus Q3. Then because 3 and 4 are in series, then Q3 equals Q4. Then Q2 plus Q4 equals Q5 also. So Q2 plus Q4 equals Q5. Q3 equals Q4. Then since pipe 2 is laid parallel to 3 and 4 combined, HF2 equals HF3 plus HF4. Then the total head loss can be set up as HF1 plus HF2 plus HF5. So these are the necessary equations for this case. Then series parallel pipes case 4, we have 3 pipes that are parallel. So for the discharge, Q equals Q1 equals Q5. Q1 equals Q2 plus Q3 plus Q4. Because 2, 3, and 4 are parallel, then HF2 equals HF3 equals HF4. Then for the total head loss, it is equal to HF1 plus HF3 plus HF5. Take note that HF3 can be replaced by HF2 or HF4. Then let's have series parallel pipes, case 5. This is the last case. So for discharge, Q equals Q1 equals Q sub 6. Q1 equals Q2 plus Q3 plus Q4. Then Q3 plus Q4 equals Q5. Q2 plus Q5 equals Q6. Then 3 and 4 are parallel, so HF3 equals HF4. Pipe 2 is laid parallel to 3 and 5 or 4 and 5. So HF2 equals HF3 plus HF5. Then finally, for the total head loss, it is HF1 plus HF2 plus HF6. And remember, you can change HF2 by HF3 plus HF5 or HF4 plus HF5 instead. So that's it. Then let's proceed to minor losses. The term minor losses are the term minor loss, or it is a conventional loss, conventional term. But there are situations where the minor losses are greater in magnitude than the major loss due to friction, especially if in a system there are so many fittings than the length of pipe which is short. That's the reason why in most pipe flows, engineering flows, there's a need that the flow must be turbulent in order to reduce the friction factor, and as a result reduce these losses, because it is important in conserving energy, especially if the system has machines. So to reduce the cost, the power cost of conveying liquids, especially from lower elevation to higher elevation. So that's the reason why there's a need that the flow must be turbulent. So minor losses are important when many fittings, transitions, and connections are present in a system. So generally, the minor losses are expressed in terms of the velocity head, and there's a factor called loss coefficient K. So its formula in general, except for sudden expansion. So for all other fittings and transitions, connections, except for sudden expansion, which has a different formula, the head loss due to minor losses minor loss is generally expressed in terms of the velocity head, and there is this important constant coefficient called loss coefficient. So the loss coefficient depends on the type of transition or fitting installed in the system. So that's it. And this K here is obtained from experiments. So there were technical people who already experimented and obtained the values of K for different situations. So let's just adapt the tabulated value provided for by those technical people ahead of us. So for sudden expansion, the formula which is unique is quantity velocity of the smaller pipe, mean velocity in the smaller pipe minus mean velocity in the bigger pipe, quantity square over 2g. So it's still velocity head, but velocity head difference. So except for sudden expansion, that's the formula. V sub s is mean velocity in the smaller pipe, so this has greater magnitude than V sub b, so over 2g. Equivalent length of a pipe that produces the same frictional loss as the fitting. So all you had to do is equate the friction loss due to the presence of pipe length to the minor loss. So F L equivalent over D, velocity head by Darcy-Weisbach, equals minor loss coefficient times velocity head. So we can cancel this velocity head. So the formula is, it is K over F times D. So it is expressed as the ratio of K over F, which represents the number of diameters. So K over F times the number of K over F is the number of diameters. So that's the formula for equivalent length of a pipe that produces the same frictional loss as the fitting. So to help you visualize the situations in a pipe systems where we have frictional loss and minor losses present, let's have these pipe systems connecting two reservoirs, and the flow is, let us say, by gravity alone. There are no machines. So fittings, transitions, and connections. So these are the different fittings, including the pipe entrance, which is what we call sudden contraction, because we have a very large reservoir. Then it enters this very small opening. So we call this entrance, loss coefficient at entrance, and it depends on the entrance. If it is square edge or flush entrance, remember it was zero point 0.5. K is 0.5, zero point 0.5 of the velocity head, velocity of flow in this pipe here. Then we have the presence of valve, then elbow, 30 degrees, 45 degrees elbow, or whatsoever. Then we have here a conical diffuser or expansion, but gradual. We have here a 90 degree standard elbow. We have a bend, by the way, here. Another bend, 90-degree bend. Then this is gradual contraction, just like a cone or a nozzle, just like that. And we have a gate valve here. And we have submerged exit, where we have velocity here, and as it enters this large reservoir here, the velocity instantly reduces to zero. Mean velocity reduces to zero as the particle or stream enters this large reservoir. So if you draw the energy grade line, this will be the resulting energy grade line. And I explain why it slopes downward in the direction of flow. Remember the principle that the energy grade line always slopes downward in the direction of flow unless there is a machine, a pump, for example. So the total energy in the system is simply the difference in elevations, liquid surface elevations. And that is also the total head loss if you add all these frictional losses and minor losses. So first, the energy level is at the liquid surface of this higher reservoir. It drops a little because of the presence of this pipe entrance, which is 0.5 of the whatever velocity head there is in this pipe. Then between this entrance and this valve here, it continues to slope downward because there is length of pipe and there is frictional loss there. So it drops, it slopes downward, then it drops again because of the presence of this valve, glow valve, and there is a table for that also. You are not obliged to memorize the table. These coefficients, loss coefficients for fittings and transitions are ready-made. So in the problem, it will be provided. You are not obliged or forced to memorize those things. Then between this valve and before the bend, it slopes downward because of the presence of this pipe due to friction. The drop is due to friction. Then it drops again due to the presence of this bend here. Then between this bend and this elbow here, it drops, slopes downward again, and the difference is due to pipe friction. It drops again due to the presence of this elbow, 30 degrees or 45 degrees, whatever. Then between this elbow and this diffuser here, we have pipe friction loss again. It drops, it slopes downward. It drops again because of the presence of this conical diffuser. And between this conical diffuser and this elbow here, 90-degree elbow, it slopes downward because of pipe friction. It drops instantly because of the presence of the elbow as minor loss. Then it drops because of the length of this pipe, vertical pipe here. It drops again due to the presence of this 90-degree bend. Then between this bend and this, before this gradual contraction, we have the presence of pipe, so frictional loss. Then head loss it drops due to this gradual contraction. Then between this and this valve, gate valve here, we have a pipe, so it slopes downward again. The presence of the pipe obstructs the flow, so even if it is fully opened, then it drops again due to the head loss due to this fitting here valve. Then before the valve and the exit, we have it slopes downward because of the length of pipe friction loss. Then upon entering the reservoir, large reservoir, it drops again. And from head loss due to sudden expansion, this is sudden expansion from small diameter to very large reservoir. So remember the formula V sub S minus V sub big quantity square. V sub big is 0 instantly, so it reduces to V sub S square over 2G. That means that the coefficient here at the submerged exit is 1 because it reduces to K V sub S square over 2G. And always, by the way, if we have different pipes, the velocity head there is the velocity head in the smaller pipe, the higher velocity head. Remember that. So we have a bend coefficient, elbow coefficient, expansion, it is denoted by Kx prime, elbow, K sub E, contraction, K sub C2, we have bend by the way here, K sub G2, then sudden expansion K is 1 as explained earlier because it reduces to just velocity head in the smaller pipe over 2G, so the K is 1. So for pipe entrance, K is, these are the values of K. Square edge, that represents 0.5 there. Rounded or bell mouth, remember the head loss is very small, so it ranges from 0.01 to 0.05. But I'm just giving you the range. Do not memorize, don't worry about it. It will be given in the problem if you are asked to solve a problem on the incorporation of these minor losses, except for major loss where you are obliged to memorize the formulas, empirical formulas. So approximate loss coefficients K for commercial pipe fittings, type of position of fittings, these are the different pipes, and the values of K. So I will not explain that anymore because anyway it will be provided in the problem. Then loss coefficients for sudden contractions. Sudden contractions is different from this one because this is gradual contraction. Sudden contraction means from bigger pipe then 90 degrees to smaller pipe. So when the ratio of small diameter to big diameter is 0, so that means it's like this one, small diameter to reservoir. The diameter of big reservoir is very high compared to the diameter of this pipe here at entrance. So it's 0, almost 0. So that's why it is 0.5, just like that. So if it is 0.1, 0.45, if the ratio of small to big diameter is 0.2, is 0.42, and so on and so forth. Anyway, if the ratio is the same, it's just like there's no contraction. It's just like a smooth connection, so that's why there's no K. That's the meaning. I hope you got it, but you're not obliged again to memorize that. For gradual expansion, just like this, so from smaller to bigger, that's gradual. These are the angle theta here, and this is the curve in approximating the value of K. In general, the formula for the head loss for minor loss of this type is a certain K times velocity in the smaller, mean velocity in the smaller pipe minus mean velocity in the bigger pipe quantity square over 2G. So for gradual expansion, this is Hx prime is K quantity velocity in the smaller minus velocity in the bigger quantity square over 2G. Just like that. But I just changed that to this. They're the same. Then that's a bend I mentioned. Then for other fittings, we have miter 90-degree miter bend with vanes. Without vanes, 1.1. With vanes, then we also have 90-degree smooth bend like this. So we have ratio of radius of curvature to the diameter of the pipe. Then with vanes, zero point 0.2. Then if the ratio is 1, then 0.35, it's 2.19. But don't worry again because it will be provided in the problem. So that's it for the discussion on minor losses. I hope that you got the point, you understand the explanations, and you're ready to solve problems involving minor losses.